now that we've covered the fundamental forces, and in particular the weak force and the strong force, we can go back and have a look at conservation of strangeness. Before we do, let's just quickly recap about strangeness. So if we've got a strange quark, it has a strangeness of -1. And again, just a reminder, the value negative is because we want to keep it in line with the charge that's on a strange quark. And a strange antiquark has a strangeness of +1. Now, if we were to look at any baryons, if a baryon contains a strange quark, then it's going to have a strangeness of -1. If it contains two strange quarks, then it would have a strangeness of -2. And likewise for if it contained an anti-strange quark or a strange antiquark. So when we talk about conservation laws, we're talking about whether or not certain properties are maintained throughout a particular interaction. So if we look at strangeness, it's not quite as straightforward as the other conservation rules. So strangeness is not conserved when we have, or when any strange particles, so particles that do have a strangeness, when they those strange particles decay due to weak force interactions. So when we're dealing with the weak force, that means that strangeness won't be conserved. So to give you an example of that, if we look at the sigma plus particle, or sigma positive, the way that it decays is by producing a neutron and a positive pion. So there's the decay equation. Now, just to identify what the quarks that are involved, so we've got two ups and a strange for the positive sigma. A neutron is an up and two downs, and the positive pion is an up and an anti-down. Now exactly what's going on there we don't really need to worry about, just want to look at the properties themselves. If we go through now and look at the conservation, we can see first of all for charge that the positive sigma has a charge of +1, the neutron has a charge of 0, and the positive pion has a charge of +1. So they are all conserved. If we look at the baryon number, now baryon being something that contains 3 quarks, so on the left hand side we've got +1, on the right hand side we've got the neutron is a baryon, so it has +1, but the positive pion is a meson, so it has a baryon number of 0. I'll skip over the lepton numbers because they're all 0 for these particles, and we'll just go straight to the strangeness. Now because the positive sigma has a strange particle in there, it has a strangeness of -1, and you'll notice that the other two particles on the right hand side have no strange particles in them, strange quarks, and so they have no strangeness. So you can see there that in that particular case that we have that strangeness is not conserved. Now we do have scenarios where strangeness is conserved, and as you may recall, I mentioned about the strong and the weak forces. So strangeness is conserved when interactions involving the strong force occur. And so that means that largely when we're sort of dealing with not just the decay of a particle, but when we've sort of got an interaction where the quarks in particular are interacting. So again, if we have a look at an example here, in this case we'll look at a proton interacting with a negative pion, and that goes to produce a neutral kaon and a neutral lambda. So again, if we look at the quark component, so up, up, down for the proton, and a down and an up antiquark for the negative pion, going to produce a down and an anti-strange for the neutral kaon, and an up, a down, and a strange for the neutral lambda. So again, if we look at the properties here, charge +1 and -1, and then that goes to give 0 and 0, so we can see that the charge is conserved. Baryon number, proton has a baryon number of +1. The negative pion, considering it's a meson, has a baryon number of 0. The neutral kaon likewise is a meson, so it has a baryon number of 0. And the neutral lambda has 3 quarks, so again it is a baryon, so it's +1. So we can see that baryon number is conserved. Again, skipping over the lepton number and going straight to the strangeness, no strange particles in the proton and none in the negative pion either. However, on the right hand side we've got a strange antiquark in the kaon, so that has a strangeness of +1, and we have a strange quark in the lambda, so it has a strangeness of -1, and so you can see there now that we do have conservation of strangeness in that particular interaction. So just one extra thing to remember there about conservation rules. So strange is not conserved with the weak force, but it is conserved when the strong force is involved.